Good morning, everyone, and welcome to week 9. We're in physical science. Today is going to be a topic which is continuation of the previous topic, namely last time we introduced charges. Today we're going to introduce currents. We're going to do the DC currents, and this is also the lab for today. So hopefully you guys will be ready for the lab, and we'll be covering a little bit more concepts actually in the lab than what we do in here, especially when in terms of the way you rearrange or arrange actually your circuit. So let me share with you basically where we are. Again, the midterm is not this week. The midterm is Wednesday, a week from, next week. So we still have about 10 days leading to that. Hopefully you guys are doing the reviews and you're going to be ready for it. Okay. So let me share my notes. So again, today's topic is about electric currents. Last time when we discussed basically the phenomenon of electricity, we discovered that particles have a property called the charge. Sure the pen is. So they have a property called the charge. And the charge happened to have two flavors, either positive or negative. And that is a convention actually, positive and negative doesn't mean much. So a positive charge or a negative charge. Two similar charges, namely two positive charges or two negative charges, so similar, they will repel. Two unlike charges, either a positive or a negative and positive. So two unlike charges, they will attract. So that's what we learned last time, okay? Also, if I have two charges, it doesn't matter what sign they are. So I have a charge 1 and charge 2, and I put them at a certain distance. If I bring the distance closer, so if I put charge 1 and charge 2 closer to one another, so in this case, the force increases with decreasing distances. And as a matter of fact, it increases by the inverse square. So this is basically what we noticed. As a matter of fact, we put it in a law that we wrote actually in the lab and also in the lecture, that the force that these two charges experience is proportional to their charges. So I'm calling Q1 in here, and I'm calling Q2 in here. So the product of the two charges divided by the distance squared, okay? But these constants happen to be in vacuum or in air to be just a number, and that number is just 9 times 10 to the power 9. And the units for it, of course, are Newton times the square of a meter divided by the square of the unit of a charge, which is a coulomb. So the unit for the charge, we define it as being the coulomb. Okay. So this is in a nutshell what we said last time, basically, that as the distance increases, the force drops, and it drops like the 1 over square of the distance. And as the charges, of course, increase, the forces increase. That if the charges happen to have the same sign, either two positive or two negative, then the product is positive and the force is repulsive. If one of them is positive, the other one is negative, then in this case, the product is negative and the force is actually attractive. And the force is actually on the same line that joins the two charges. Meaning, if in this case, the force can be either a repulsive in this case, the two charges are repelling one another, or it can be attractive, of course, depending on the sign. But the point being in here on the axis that joins the two charges. So it's going to be collinear with the same axis that joins the two charges. So this is in a nutshell what we discovered last time. Also, we discovered the concept of the electric field. The electric field happened to be the force per unit charge, okay? So if there is a region of space where I have a distribution of charges in here that produces an electric field of some sort, the electric field, because the charge in this case is not uniform, the electric field may look kind of not similar to the point charge where I drew it nicely and all of that. But the point being in here, if I bring a charge Q, so there is a region of space that has an electric field in it. So if I bring a charge and the electric field happen to be pointing in this direction and this point in here, if I bring charge Q in here, that charge will be subject to a force. That force is the charge times the electric field. Obviously, I drew the vector on top of the F and the E because both of these two quantities are vector quantities. The force is, of course, a vector quantity. The only reason I didn't write the vector symbol in here because I'm assuming that it points away from the charges on the same axis in here, or points toward the charges on the same axis, depending on if the charges are the same sign or opposite to one another. But in general, it's a force that is proportional to the electric field. In the same token, we introduced the concept of the electric potential that time, and the electric potential, which is denoted by U, is actually, so this is the potential, the electric potential, I should be more specific, electric potential. And the book uses the symbol PEPE, electric potential energy divided by the unit charge. So the units for the electric potential are the same as that of the energy, which is in this case electric potential energy, which is joule, always the unit for energy is joule per coulomb. Actually, we gave it a name in honor of Mr. Volta, we gave it the name of volts. And this is what you hear a lot of people talk about when they talk about a 1.5 volt battery if you go to the store and buy it and so on and so forth. It's the same idea. So this is the electric potential, and that's exactly what the power company delivers to your household or delivers to your place of work, and that there is a plugs that have all of them 120 volts. With a promise that if you connect a device to it, it's going to drain energy, and that energy is going to be at the rate of EPE, which is just the amount of charge you drain times that potential that the power company delivers to you, which is sometimes like 120 volts. So if you drain 1 coulomb, you're going to get 120 joules. If you drain 1,000 coulombs, you're going to get 120 times 1,000 joules. That's basically in a nutshell what that entire chapter 20 is. Okay. We also discussed power, but we're going to discuss this power again today, which is the amount of energy that is consumed per unit time. Okay, since we're dealing with time, there is another concept that we're going to introduce immediately in this case, and that is the concept of current. And this is actually the topic of chapter 21, okay? So what is a current? It's the amount of charge that flows per unit time. So current is the amount of charge that flows per unit time. So if I take a wire of some sort, I'm going to take a wire and I'm going to look at it with a microscope. So it looks like this. Obviously, this is part of a wire. This is not the entire. The wire extends this way and extends both ends. Okay, so this is part of a wire. Not the entire wire, because the wire extends very long, and I just took in the region of it and I looked at it with a microscope, so it looks big. So it's of cylindrical forms of some sort. So it has a cross section, and it has a length. So it's of a cylindrical shape. Obviously, you can twist the wire whichever way you want to, and you can have all kinds of things. And if I take as a region of space in here, it doesn't matter which, this one in here, and see, or they take the entire component, and see how many charges I have in here. Typically, I'm going to take, for example, a charge Q, and I'm going to monitor it, okay? So this is a given amount of charges. I'm counting them in here. Let's say we have 7 charges, okay, in my wire. Obviously, the number is very tiny. It's usually, I mean, the number is very, very big because I'm taking in here this number, which is small. The typical number is a huge one, 10 to the power something, okay? Big number also. So the point being in here is if I wait for a second and nothing happens, then in this case, there is no current flow. But if all of a sudden the charges start to move, this charge moves from here to this point, this one moves to this point, this one moves here, this one moves here, this one moves here, this one moves here, this one gets out completely, and this one is here, and another one jumps in from outside. So in this case, there is a flow of charges, just similar to the fact that if you have a hose, for example, without, and let's say, for example, it's sealed from both ends, okay? I mean, you turn on the water from the other side, but it's sealed. There is no water running through it. So there is water inside of it, but because it's closed from both ends, there is no flow of current in this case. There is no charge going, there is no current in this case. But if you decide to all of a sudden to open the faucet from the other end that releases the water, now water starts flowing. So this is an analogy with that. So this is what we call a current. In this case, I can say that I definitely have current of charges. So the current of charges, the symbol for it is I, by the way. So this is the current, is equal to the rate at which charges change. So the number of charges either increasing or decreasing in a region. So this is the delta whenever, and we discuss this symbol a lot. So this is delta, the Greek letter delta, which stands for change. Just like when we did, remember, the velocity was delta x over delta t, the change in position over change in time. This is the same thing, the change in charge over change in time. So if I wait a second and I see that this number is changing, then in this case, I definitely say I have a current. If this number doesn't change, that means I don't have a current. This number can also change in two ways. It can increase, it's going to be positive. In other words, it can flow to the right, or it can flow to the left. So depending on how you look at it. So this number can be positive or negative, okay? So depending on which way you're pushing your charges, they can flow one way or the other. So in other words, take of a hose, for example, you take a hose and you flip it, okay? If you can do that, then the water can still run, but it's going to run in the opposite direction of the hose in this case. So that's in a sense what's going to happen. So, or you take a hose full of water, after you fill it with water and you hold it from both ends, now you lower one end, is going to flow this way. But if you repeat the experiment but lower the other end, now it's going to flow in the opposite direction. So that's basically what's going on in this case, okay? So it's the flow of current can be one way or the other. In other words, if you decide on the direction being positive, always from my left hand to my right hand is positive, then in this case, the current is definitely negative, or in this case, definitely the current is positive. So that's basically in a nutshell what that means. So this is what the current is, and it helps to have a battery. So the first thing that we're going to introduce in here is the concept of battery, which is very, very important. And that's how the book starts with. Before I move any further, the units in here. Obviously, the unit of the current is that of the unit of charge, which is a coulomb, divided by the unit of time, which is a second, okay? We gave it a name, actually, in honor of Mr. Ampere. This is called the ampere. A is ampere, and you hear this word a lot. Ampere has an accent in it, the French thing, ampere, actually, its name. But you hear the word amp a lot when you go to Home Depot or something. How many amps is that thing, or whatever that thing is? How many amps that wire can support? Okay, that depends on the gauge of the wire. Otherwise, it's going to burn. It's going to smoke. So in this case, that's the unit for the current. The unit of the current is one of the fundamental units in physics. Remember, there is the meter, which is the unit for length. There is the kilogram, which is the unit for mass. And then this is the unit for second, for time. And now, the unit for current, which is ampere. So those are the four fundamental units in physics. So which means that Coulomb actually is not a fundamental unit. The Coulomb is actually a derived unit. The Coulomb is 1 amp times 1 second. Remember, A and S are both part of the fundamental units. So 1 Coulomb is not a fundamental unit. but rather a derived unit similar to Newton. Remember, a Newton is 1 kilogram times meter per second squared. And that is actually the meter is here, the kilogram is here, the second is there, except they have a combination involving the second square ratio and so on and so forth. That's all. So that is another unit that we have seen so far is the joule. 1 joule is 1 Newton times 1 meter. That's a force times distance. The force is in Newton, and Newton itself is not a fundamental unit, just a Newton kilogram meter per second squared. So this is a kilogram meter per second squared times meter, so that makes it kilogram meter squared per second squared. So the joule also is not a fundamental unit. Newton also is not a fundamental unit, and also a Coulomb is not a fundamental unit. So those are the fundamental units that we have. They are derived units, and the fundamental units is MKSA. Anyway, so these are some of the word about the units. So the current is in amp, and amp is a fundamental unit. So it helps to have a battery before we start talking about circuits. So what is a battery? I know the book starts with the historical context and how Mr. Volta basically discovered and built the first battery. And in a nutshell, what that is basically you have two metals. So each metal, so the wire I was describing earlier that allowed the current to go through, it is a metal. And usually it's copper. That's what you go and buy from the store. So it's copper, and copper is a good conductor. But you could use iron if you like. Iron is a poor conductor, but you could use it. You could use gold, actually, which is a very good, even better conductor than copper. You could use silver, which is better than copper, but less than gold, and so on and so forth. So those are some of the materials that are tin, also aluminum. All of these things are metals. So it helps to understand what the concept of a metal is and how that plays, okay, into this constitution. Usually it's zinc involved. Zinc also is another metal. So what's going on in here? There are two kinds of materials. Either it's a conductor or an insulator. There are some weird materials that can do both. And there are certain conditions. And there are certain conditions they could be insulators, and there's some other conditions they could be conductors. And those are the so-called semiconductors. Semiconductors are so important in industry that no electronics can survive without them. I mean, most of your, not most, all of basically the most component of your cell phone, your TV, your computer, your watch, all of electronics depends on semiconductors, which sometimes they like to do it one way, sometimes to do it the other way. And there is another fourth class of materials called superconductors. But for right now, we're focusing only on these two. There are conductors. Basically, what's the difference between a conductor and an insulator is a conductor conducts electricity. Insulator does not. That's in a nutshell what these two are. One of them is a conductor, the other one is an insulator. For example, if you go and buy a wire from the store, for copper, for example, from Home Depot or whatever your shopping place is, so you're going to find the wire, but you notice that the outside of it is actually plastic. So the plastic is actually an insulator. And the inside, the copper itself, is actually a conductor. And there is a reason for that, because you don't want to be electrocuted every time you just want to move the wire around. Besides, if the wire is exposed, it could lead to sparks, it could lead to all kinds of shortages, and the current will not work. So you need both of them, actually. You need both conductor and the insulator to work together. Okay. Wood is typically an insulator, plastic is an insulator, air is an insulator, and also conductors include this materials that the few I mentioned, okay? Each conductor has an affinity to electrons. So each conductor likes its electrons, okay? So here is a metal. So I have a metal in here. Inside the metal, doesn't matter, you have atoms. I'm going to draw a few of them in here. Random positions. Atoms has two components in them. They have nuclei. So this is the nucleus, and they have the outer shell that has electrons. Of course, there are inner shells also, and those inner shells have electrons that are well anchored into their atoms. So they are not going to move. It's the outer electrons that have the ability to move. So think of the atom as being basically a core, a nucleus, and that core includes, of course, the nucleus and the inner shell electrons. The inner shell electrons are not free to roam. There is only the outer shell electrons, the valence electrons they are called. Those are the ones that are free to move. Let's say, for example, each atom gives up one electron that it contributes to the community of electrons for that metal. Now, here is the deal. Those electrons, the minute that the metal forms, they don't belong to that atom anymore. So this electron and this one and this one, all of them, they belong to the community of atoms in a metal. So they are not, they become communal electrons. So they belong to the entire community of atoms, meaning each atom does not really label its electron that this is mine, nobody can tangle with it, as long as there is an electron that comes in and fill in the gap. So if this electron decides to move this way, for example, this one can jump in to fill in that gap. And if this one decides to move, this one can jump in and fill the gap. If this one is, for example, moved to fill that gap, this one will come in here. And if this one moves, then this one probably will come in and fill that gap. And if that one moves, this one will fill in the gap. If that moves, this one will fill in the gap, and so on and so forth. So in a metal, the electrons, due to thermal agitation, normal temperature, we were wondering what happened to this one. Well, this one probably is the one that got this one. Okay? So in other words, at the end of the day, the electrons, they don't belong to a specific atom, but each atom requires to stay neutral, to remain neutral. So if one of them moves, and they move because of temperature, because of heat, because of normal conditions. So in a metal, think about it this way, you have electrons moving every which way, going all over the place, okay? And that is the difference between them and an insulator. An insulator, they have their electrons, they don't take their electrons and put them in the community. So each atom in an insulator, so I'm going to take, for example, a wire that is made out of plastic. Each atom holds to its electrons. So there is no such a thing of, so no electron can move out. So all of them, they are actually part of it. The atom stays neutral. So the charge is still zero for each atom. And by the way, it's still zero here too, except it's still average zero. One of them moves, the other one is replaced immediately. So on average, it's still zero no matter what you look at it, as long as there is no electric potential, as long as there is no battery. If you take this one in here and put it in their battery, then the charges start to move. This one will move across the battery pushes back, so the wire stays neutral as the charges are moving, because the minute one of them leaves the metal, another one comes in to fill in the gap, and everybody will move accordingly so that the atom stays neutral. This one, though, if you put a battery in here, cross it, nothing is going to happen unless you exceed a certain voltage. in which case you lead to the breaking. You know, the lightning, because the air is neutral, and as the clouds start to rub against one another, they build charges in them. Obviously, the lower end of the cloud is different charge than the upper end of the cloud. So, and there is lightning that actually happen in the cloud itself. But there is lightning that starts to happen on the ground. So the air between the ground and the air and the cloud is neutral. But as the charge builds up so much in here, there is a negative induced charge on the other side, or a positive depending on the cloud side. That leads to discharge, electronic discharge. So if the voltage is high, this one could lead to discharge also. Okay. But this one, you don't need a high voltage. Any voltage would do. Any voltage would do to conduct electricity on a wire, on a metal. So this is an insulator, and that's a metal. So again, what I was talking about in here is the affinity. Depends really on how much communal each atom is. For example, gold can have its electrons much easier to move than, for example, copper or silver. Silver is better than copper, and copper is better than iron, and so on and so forth. So what Mr. Volta did actually discover when he was doing that, if you take an acid, for example, like a lemon, and you put different metals in here on both ends, different metals, not the same metals, each one of them would want to have its electron attached to it as an affinity for electrons that is different than the other one. So this one will free up its electrons, this one will free up its electrons, but one of them will free up more than other. And then all of a sudden, I have the ones that loses more electrons will be positive, and the one that does not leave that many charges, basically puts in, but not that many, is going to be a negative terminal. So this is called a terminal. In this case, it's a positive terminal, and this is also a negative terminal. So that's a battery. When you take a battery, you look at it, usually they're labeled properly, positive or negative, depending on the types of metals that you have in them. Now, you have a battery, because if you connect this wire via conductor here, the charges starts to move through the wire. Actually, the current flows in the opposite direction by convention. Okay, so the current starts flowing through the metal. But the minute it hits this metal, it's going to again discharge in the same fashion, as long as there is enough juice still in here, as long as there is enough power in the battery. So the batteries are labeled from 1.5 and so on and so forth, volt to 3 volt, 9 volt battery, 12 volt battery for the car, and so on and so forth for the vehicle, and so on and so forth. So this is basically how you start electricity. It's based on battery. For all we care about here in this class is that there is a battery, and what a battery is an internal mechanism to build the difference in potential between its terminals. So each battery has a terminal, has two terminals. Positive or negative. That's it. Positive and negative. So it has two of them. They're separate. So this is how the battery would look like. Positive on one end and negative on one and the other. So the current will flow from positive to negative if you close the circuits. So think about it. You have, for example, a material in here that sits between it, and you have a switch. If the switch is open, so this is a switch. If the switch is open, nothing happens. The charges cannot move because they cannot go through the air. Air is insulator. Now, if you close the switch, when it's closed, when the switch is closed, then current starts to flow. It's always flowing from positive to negative. Current flows from positive terminal to negative terminal. Okay, have a battery, of course, provided the circuit is closed, provided the switch is closed. So think about it. If you go to the switch and you turn on the switch, what you're doing, you're closing the circuit. Now the current will flow. If you open the circuit, basically no current will flow. Okay, so that's basically in a nutshell how this thing works. If you have your cell phone and you push on the power, so what you're doing in actuality, you're closing the switch. When you push on it again, you're opening the switch and the current will not flow through the system. So that's all the battery we care for. We don't want the history of it. We don't know how Mr. Volta discovered it. We don't care that much, honestly, about it. Although probably in a conceptual manner, you really need to read the units in chapter 21 so that you have an understanding of how those things are, so that you can do these questions in here. Otherwise, this is what the battery is. So think about it, okay? Here is how the analogy with it too. Think of a pump. And you have a reservoir of water, and there is a pump in here. And the pump will pump the water over a hill. And that water will later on let go to come down the hill again on its own. And then when the water reaches the pump will push, the pump is in here. The pump will push the water again. Usually it's inside the reservoir because somehow it needs to drag the water out, okay? So it takes the water through the pipe, then it's used, and then it's going to be recycled again. So this is basically how the analogy is. There is another analogy, useful analogy, and that is a bunch of people on a ski resort. So you have an elevator in here, elevator. So when the skiers come down the hill due to gravity, the minute they are here, they somehow are on the same level. So in this case, there is no work involved because you are on the same level. So the minute they reach this point in here, or they can be dragged actually by the same mechanism in here, and then raised up again by the elevator. Once they are there, then they come down on their own in here. Obviously, there are trees in here, and trees can slow down their path as they're coming down. And we're going to talk about the concept of resistance similar to this fashion here, similar to what's going on in this trees analogy. So this is in a nutshell what the whole idea of a pump is. Okay. I mean, what a battery is. So that's the idea behind it. And again, as I was saying, there are two types of materials, conductors and insulators, and that's how the battery basically functions. There is actually a little bit more to say about conductors. Conductors are not created equal, have resistance. And this resistance depends on several factors. First of all, the first one is the type of material. As I was saying earlier, gold is a good conductor. That means its resistance is low compared to silver, which is low compared to copper, which is better than iron, and so on and so forth. Okay, so the material matters. The second thing that depends on it is the length of the material. The longer it is, the more resistance you're going to have. And finally, it depends on the cross-section, how thin it is, okay? So here is all of it basically summarized in a nutshell. So again, I'm going to take that part of my conductor in a cylindrical form in here. Again, the longer this side is, the more it takes for a charge to travel. So the resistance in this case increases with length. Now, if I make this cross-section wider, obviously I can squeeze in more charges than when it's narrower. So the bigger the cross-section, the less resistance I'm going to have. So the bigger the cross-section or the area, it's the same thing, the less resistance the conductor has. So those are the main things. The first one is a type of material. The second is the length. The longer the wire, the more resistance. Finally, the cross-section. The wider the wire, the wider, not the longer. So the first one is the longer the wire, the more resistance. Now, the wider the wire, the less resistance, because, so think about it in the case of analogy with water too. If you have a narrow hose, it's going to conduct less. I mean, the water tries to squeeze through it, and it's not going to be as much as if you have a wider hose in here, flowing with the same rate. Let's say, for example, you're supposed to get 1 cubic meter of water per minute, for example. Okay, in this case, 1 cubic meter per minute will result in a very, so you actually potentially could have more in this case, because you could squeeze far more than what you would in the first scenario. Okay, it would flow much, much easier on the wider region than the first one. But if the hose is very, very long, so again, there is going to be far more from the pump to push the water through it to get you the same rate of 1 cubic meter per minute, for example. Okay, so this is the analogy with liquids, and it holds true also for the case of electricity too. So this analogy is true in this case with the material. So 3 factors: the type of material, the more resistive the material, the higher the resistance. The longer the wire, the more resistance. The narrower the wire, the more resistance, or the wider the wire, the less resistance. So these are the key concepts in here that needs to be introduced in here. So how much is this resistance is related to the current? This is given by Ohm's law. Mr. Ohm tried to understand what makes the charges to move from in the conductor from end to end when you put them across a battery. So what he found was what makes the difference is the voltage difference between one end and the other. So the voltage difference, it's like a height, for example, of the case of the wire. If you, of a conduit, for example, for liquid. If you put them in the same height, exactly, there should be no flow one way or the other. But if you take one end and put it at a much, much higher region than the other, the water will come very fast. So if you think about it, if you have to pour, for example, water out of a cup and you barely tilt it, it's going to have some flow, but not as much if you tilt it a lot. So in this case, the force of gravity plays a role. So that's the analogy with a liquid. So in this case, the voltage difference that matters, okay, between one end and the other end of the battery, one end or the other end of the wire. And what provides the voltage difference is that same battery. The 1.5 volt battery will provide a 1.5 volt drop between the ends of a wire. The 3 volt battery will provide twice as much. 120 volt battery will provide so much compared to the first one, okay? About 80 volt drop, basically, 80 times 1.5 volt battery. So again, that's going to drive far more current than the 1.5 volts. So that's really the analogy with this one here. So what matters really is the voltage drop. So again, what Mr. Ohm has discovered is that the current is proportional to the voltage drop. So this is the voltage drop between the ends divided by characteristic value of this material, which is called the resistance now, divided by the resistance. So this is the same current that we talked about earlier. So this expression can be written as V equal to IR. So the voltage is equal to IR. This is in a sense similar, but not exactly correctly to say that it is the same as the F equals to MA. So in this case, the higher the resistance, the less current you're going to end up with for the same voltage drop. Obviously, for more voltage drop, you're going to get more current, in this case, flowing. So the relationship can be expressed in this form, which is a cause and effect form. So the cause in this case is the voltage drop or the voltage difference, okay? And the effect in this case is the current that is going to be taken. So if I have a wire sitting minding its own business and I don't provide it with a voltage drop, there should be no current in it, I equals to 0. But if I somehow put a voltage drop in such a way that there is a voltage in here that is higher than the other end by a factor, for example, of 1.5 volts in this case, okay? So the current should flow in this case, in this direction. Voltage drop. So this is the voltage drop. So this is 1.5 and this is 0. So this is higher. So basically take a wire and put it this way. So it's going to come from high to low. So it's going to flow in this direction, okay? So this is the voltage drop that we were talking about in here. And that is basically what this expression is. Obviously, there is a word in here about the units, or again. So the voltage is in volts. The current is in ampere. And the resistance then has the units of volts over amps. Again, in honor of Mr. Ohm, the unit for the resistance is called an ohm. And the symbol for the resistance unit is the capital Greek letter omega. So this is the capital omega. So this is the unit for the resistance, okay? So the capital omega, and it's called an ohm. You read it as an ohm. You don't say it's omega. So that's the unit for the voltage, okay? So again, in the typical circuit, what you have Ohm's law, and Ohm's law gives me basically the current that flows for the same value of the voltage. From here, we should be able to find this value in here. Hold on, guys. Let me pause quickly in here, and I'll be back. Again, basically, let me continue this discussion. We're going to end shortly quickly here. So let me go and share. So again, it's the resistance, which is in ohms, that is characteristic now of a circuit. So in the lab, we're going to talk more about these things in the lab. We're going to explore these ideas further and basically see how we can arrange wires depending on the resistance. Every material has a resistance, no matter how good it is, including a light bulb. What a light bulb is, in actuality, is actually a resistor. Okay. And the resistance has in its property something has to do with the power. So, and that is the next concept in here that we need to talk about, okay? And that is the concept of power and energy that is dissipated. So the power, and I think we talked about that last time too, we defined it, is in this case voltage times current. So this is the power. Okay, power is voltage. Actually, I should call it difference in potential. That's what the word for voltage is. So I know I'm using that word loosely. The difference is the difference in potential, which is the voltage. Okay, potential times the current. Okay, this is what you see labeled on all of the devices is the power they consume. So the power is in watts. That's the unit for power, okay? That's the unit for power. And the voltage is in volts and the current is in amps. So all of these things, they fit together now. That is what you see when you go and buy a light bulb. If a light bulb is labeled 40 watts, that means going to consume 40 joules per second. That's what the power is, okay? It's the amount of energy consumed per unit second time. So for the case of a resistor, it's easy to find because the voltage is equal to IR, and you multiply it by I, another I, so it's gonna I squared times R. So for a resistor, the power is equal to I squared times R. Obviously, the power, 60 watts, for example, light bulb, doesn't tell you how much energy is consumed. It depends on how long you leave it on. If you leave it for 1 second, well, it's going to consume 60 joules in that case, because again, if the light bulb is 60 watts, then how much in 1 second? Then in this case, you just multiply 60 by 1, and you're going to get 60 joules. But if you leave it for a day, that means you have to multiply that number by 24 hours. And an hour has 60 minutes, and a 60 minutes has 60 seconds. You have to multiply it by this number to get, so it has 60 watt light bulb. You have to multiply it by 24 times 60 times 60 to get how many joules at the end you're going to consume. So you have to be careful in here. Usually, the power company does not charge you by joules. It charges you by kilowatt hour. Okay, that is how the power company charges us, by kilowatt hour. Kilo is 1,000 watts per hour. So the power company doesn't charge you for the voltage. It doesn't charge you for anything. It charges you how many watts you use per hour. Doesn't matter how many thousands of watts you use per hour. That is how the power company, and that is energy. This is energy, because when you multiply watt by hour, it's going to be an energy, except that they don't use it in joules, because a joule is going to be a big, huge number in terms of kilowatts per hour. Okay, I need to stop right here, actually, because we still have a lab that we're going to discuss some of the interesting stuff related to it later on today. And then when we meet on Wednesday, we're going to get a little bit more numbers, because it's important to understand the circuits. This is the DC circuits, direct current circuits. Just a quick word on it. So the D stands for direct circuit. And there is a little bit more probably talk later on about the AC circuit. And I know I mentioned so many alternatives. I mentioned several times today the fact that the power company delivers 120 volts, and usually that 120 volts is not a fixed voltage. It's not DC anyway. It's actually an alternating current. Okay, alternating, I should say, current. It's a current that goes like a sine wave. Okay, at some point it's a very high voltage, and at some point it's a very low voltage. Effectively, as if it is DC current, as if it is a direct current, not really, as if it is DC current with a value that is 120 volts, okay? 120 volts is shy of the maximum by a few factors in here. So the maximum is actually around 170 volts, but you need to have it effectively running as if it's steady. So the 0 is here, as if it's not changing at all, as if it's 120 volts. Because it happens so fast. Because it happens 60 hertz, 60 times. So these fluctuations in here between minimum and maximum takes place 60 times per second. That's the frequency of the current in the United States. This is in the US, of course. in the US, the current will go up and down, up and down, up and down 60 times per second, fluctuates. So the two ends that you have, the terminals that you have in the wire, they change back and forth, 60 times per second. This is as opposed to the rest of the world, which is a different convention. Most of the world anyway, they use actually, the voltage is not 120, but 240 volts. So twice as much as this, but the frequency in the rest of the world is only 50 hertz. So it goes 50 hertz back and forth, 50 times back and forth actually in 1 second. So that is the difference. So this is the frequency of the current in the United States, and this is the effective voltage, okay? So I'm not saying it's a maximum. The maximum is slightly higher than the effective volts. But if I talk about maximum, I have to talk about minimum. And then at any given point in time, it could be anywhere in between them because it's a sine wave function. Whereas in the rest of the world, also it's a sine wave function, except the maximum is happening as a much, much higher than this one, 340 to be more specific, effectively running as if it's a steady current of 240, twice as much as that of the United States, okay? So this is, in a nutshell, basically the introduction to this unit. I'm going to have more discussion down the road on Wednesday. I'll see you guys then. And we also have a lab today, so hopefully we'll cover all of the relevant topics to it. Thank you.